Good morning to all. Myself Dr. K. Manoharan, Associate Professor, Department of Biomedical Engineering. So today class we are going to discuss about ADC interface. So ADC is an analog to digital conversion. So the real world signals are in analog nature. So we cannot directly interface this analog to the microprocessor. So that's why we need to convert this analog to digital. So for that we are using this analog to digital converters. So general algorithm for ADCs, we use two connections, that is two signals, EOC and SOC. So start of conversion and end of conversion. Look at this. So first thing, ensure the stability of analog input applied to the ADC. Because only if you have a stable input, so that corresponding analog input should be converted to digital. So first we need to wait for some seconds, so whether the input to become a stable. After that, we can give this SOC, that is a start of conversion pulse to the ADC. Once this ADC receives this start of conversion, it start convert the corresponding analog input present to the digital. So read the end of conversion signal continuously whether the conversion is completed. So after completing the analog to digital conversion, ADC gives an end of conversion signal to the microprocessor. So microprocessor need to wait that till end of conversion signal reached from an ADC device. So once the ADC signal, that is end of conversion, is received from an ADC device, so it can read the data from an ADC, that is an actual data present in that. Look at this black diagram. Look at this. So this is an 8-channel analog multiplexer. Actually, one input can be analog input converted to digital. So instead of that, we taken 8 inputs. So at a time we cannot convert all 8 inputs. So we can choose any one channel. Here look at this. We have an 8 channels. So that means we have an 8 analog inputs. Any one analog input will be selected by using these address lines. So look at this A, B, C. So this will be from 000 to 111. We have an 8 combinations. So depending upon this 8 combination, this any one input channel will be selected. That means this will be 0 means this input channel 0 will be selected. 001 means channel 1. 010 means channel 2. 011 means channel 3. 100 means channel 4. 101 means it's a channel 5. 110 means it's a channel 6. 111 means channel 7. Any one input channel will be selected. That channel in analog input should be converted into digital. Look at this, we have a comparator here, and then we have this SAR, successive approximation register. So for an ADC conversion, we have so many methods. So the best method is successive approximation. So because for converting from analog to digital, it takes some time. So we need to have a faster response. So we get it a SAR method, that is a successive approximation register. So here actual values will be decoded within this bit size. If it is a 4-bit, within the 4 cycle we get the complete results. Look at this, this is an actual input and this is the reverse. So this will be compared. Based on that SAR can be incremented or decremented. So look at this, this is an SOC, start of conversion. After completing, it gives that EOC pulse. So look at this. Actually operation is first we give this SOC pulse. Once if it receives the SOC start of conversion, so that corresponding input channel will be read depending upon this input, and that will be taken, and then SAR will be set to one value. So this value again converted back to analog and given to this here. So now this input and this output will be compared here. So depending upon that, the input may be high or feedback input may be high. Depending upon that, the next value will be 1 or 0. So that means, for example, it is a 4-bit. Normally we have an 40 to 41. So first now we take a first bit will be 1. So second bit will be 1 or 0 depending upon that whether it's a greater or lesser. Lesser means the first bit will become 0 and then second bit become 1. If it is a higher, first bit also 1, second bit also become a 1. So this operation will be repeated till it reaches the equal value. So the second bit will be set. Again it compare with that analog input whether it's a higher or lower, depending upon that will be 1 or 0. Again this will be repeated. So within that 4 cycle of operation, it completes the data and gives an end of conversion. So once end of conversion is given, that means actual input given here, that will be available, it has an output pins. Once this output pin will be data available, it can read this. So if you use instead of SAR any other methods, it takes lot of cycles. For example, if you take an increment method, so from 00 to 111, it will be increments. It takes up to 16 clock cycles to get an actual values. But if you take an SAR method, I am saying it for a 4-bit. If you take a 4-bit, any other register, it may take up to 16 clock cycles. But if you use an SAR method, successive approximation register method, within 4 clock cycles, it gets the speed. So look at this, 16 and 4, around 400 times faster the operations. So that's why SAR will be preferred in all analog to digital conversions. Look at this operation. This is the clock pulse given to the successive approximation register. This is the actual data bits, and this is the given for an DAC. This is the reference voltage. So here we are giving this comparator. So this is the input voltage and this is then output voltage. So these two will be compared depending upon whether it's a greater or lesser. So it will be becomes an SAR register will be changed like that. So within 4 clock cycles, it completes an operation, gives then EOC pulse. Look at this, how it will be interfaced. So we cannot directly interface an ADC2 with the microprocessor. That's why we are using this 8255, and then we are using this port A as a data bus file, and then for a channel selection we use this PB, port B0, 1, 2. These 3 signals will be used for selecting that particular channels, and then port C pins, PC0 will be used as a start of conversion, and PC7 that will be used for an end of conversion. Thank you.